Hello and welcome to lecture number 20. So in today's lecture we are trying to derive the BET theory itself. Okay, so let's start with the model of the BET theory. As I have already explained in the previous lecture that both monolayer and multilayer adsorption goes on simultaneously according to the BET model. So if we look at the adsorption surface, so this is the solid surface where an incoming molecule would find an I number of different options to sit on. For example, there are places where it can sit on one number of means top of one single molecule, or a top of two molecules, a top of three molecules, or top of I number of molecules, or top of zero molecule there. So therefore we can assume that the incoming molecule has I number of options to sit on, where I is the number of layers. Alright, so therefore I can be 0, 1, 2, 3, etc. and that may lead up to infinity. Alright, so there are infinite number of options for an incoming molecule to sit on. Alright, so now that we can understand, so what is our purpose? So the purpose of BET theory is to, like Langmuir's theory, is to establish a relationship between N, that is the number of gas molecules adsorbed, with the pressure of the gas molecules being adsorbed. So this is N versus P relationship. So how to connect N and P? So the N and P should be connected with theta. So that's what we exactly did in case of derivation of Langmuir's adsorption isotherm. So theta is the fraction of gas molecules adsorbed, right? That is N over Nm, that is number of gas molecules required to cover a complete monolayer. So the N versus P relationship has to be established through theta. So there has to be an expression for theta. So similarly, here we would like to find out what are our different theta values are, because in case of Langmuir's model there was only one theta, but here there are multiple theta values. So let's try to figure them out. Okay, so we have first theta 0. So that means that is the fraction of surface covered by zero number of molecules, zero molecule. Okay, and then again we have theta 1, that is fraction covered by one molecule, theta 2, fraction covered by two molecules. Similarly, we have theta I, the fraction covered by I number of molecules. All right, so this is clear. Very good. And also, since the total fraction should be 1, so the summation of theta 0 up to theta I whatever should be equal to 1. So therefore there should be also another relationship, that is theta 0 plus theta 1 plus theta 2, like that we can go up to theta I plus etc. whatever the theta's theta is there, should be equal to 1. All right, so this little relationship we can call it equation 1. All right, so you may understand that there would be several such equations. So therefore, in order to identify, we call it equation 1. And not only that, so now we just have to understand a little bit that what is the significance of theta 0. All right, now let's think about the Langmuir's model. All right, so in Langmuir's model, so we have this whenever we have a complete monolayer, that means only one molecule is sitting on the surface and the monolayer is complete. So complete monolayer. Okay, so how can I find out the expression for N, that is number of molecules that is required to have the complete coverage. So according to BET model, we can express this number n something like that. That is theta 0, all right, plus 1 theta 1 multiplied by nm, all right. So that means here in Langmuir's model, where we are in the process of forming only monolayer, complete monolayer. So what happens? N is equal to theta 0. So here theta 0 is essentially 0 because we have not a single fraction that is uncovered. All right. So for a complete monolayer, theta 0 is equal to 0. And for every fraction covered by one molecule, okay, so for every theta 1 we have one molecule, all right. So therefore we can easily come back to this situation, that is n is equal to theta 1 multiplied by nm, or n by nm is equal to theta, all right. So this is what our understanding of the Langmuir's theta in the light of BET assumption. So therefore this consideration is for monolayer only. So what we understand, that for a complete monolayer, now this is very important, that for a complete monolayer the value of theta 0 is equal to 0, because there is not a single place like this where no molecule is sitting. All right, so we have to understand that. Having said that, the most important scenario when we come at this situation, that is the BET situation. In BET situation, we can write that for BET model, we must have to understand one thing, that is theta 0 is not is equal to 0, because we have certain fractions of places on the solid surface where there are 0 molecules. Okay, so theta 0 not is equal to 0. It should have a certain finite fraction. So therefore, for BET model, the total number of gas molecules n, how can it be expressed? So these can be expressed by this number, that is 0 molecules on theta 0 plus 1 molecule at theta 1 plus 2 molecules at theta 2. Okay, so this is so 2 molecules here, so whatever the fractions covered by 2 molecules is theta 2, and since we are finding the number of molecules, total number of molecules, so we have to multiply by this number plus I theta I plus etc multiplied by nm. So that gives us the number of gas molecules adsorbed at any time. So n should be equal to these fractions multiplied by nm. So now what we can do is we can express this summation into a mathematically shorter form, which is summation, okay, so 0 theta 0, so 0 multiplied by theta 0 means 0, so we can neglect that term. I is equal to 1 to infinity I theta I multiplied by nm. Okay, so here you see we get one more equation, and we call this as our equation number 2. All right, so we have here equation number 1, and also we have equation number 2. And what is most important thing is that this expression can also be expressed something like that, I is equal to 1 to infinity theta I plus theta 0. All right, so yes, so theta 0 plus I is equal to 1 to infinity theta I is equal to 1. All right, so this is another form of equation 1. So finally we have these two consolidated expressions for theta. So why we are doing that? So now we can connect in some way n, there is number of gas molecules adsorbed at any time, with some kind of theta. So what is our next job? Our next job is to relate this theta or n with the pressure of the gas. So that's our goal. So for that, we have to go back the very basic thermodynamic consideration, as we have used that for, because the basic science is the same. So as we have used the same thing for Langmuir's model, we have to apply the same understanding thermodynamic consideration here in BET theory. So what was that consideration? So that consideration was that at any point of adsorption, it goes through establishment of equilibrium. So that means at any point, any time, the rate of, we should not call it at any time because it is time independent. So we call it at any stage, the rate of adsorption is equal to the rate of desorption. All right. So that consideration will give us many equations through which we can relate theta with the pressure P. All right. So having keeping these two equations in mind, now I'm going to erase the board and we are going to start the next part of the derivation from the thermodynamic consideration. All right. So let's do that. So as our goal was to establish a relationship between the theta and the pressure P, so we have to go back to the fundamental thermodynamic consideration, that is, at any stage of adsorption, rate of adsorption is equal to the rate of desorption. So if we follow that, then there are several different scenarios come out. All right. So we start with case 0. Case 0 means only one molecule coming to a fresh surface. Okay. So that means the surface is totally empty. So the molecule would sit to form a single layer. So for case 0, the rate of adsorption is equal to the rate constant of adsorption, Ka is 0, we can call it here. Okay, because this is for the 0th layer, multiplied by the pressure of the gas P, multiplied by the fraction of gas molecules with 0 molecules on it. Okay, so that is theta 0 essentially is equal to K d0, okay, multiplied by the fraction of gas molecules that is already occupied by one molecule, that is theta, obviously theta 1, multiplied by e to the power, so this comes from the Boltzmann distribution actually, e to the power, and also from the Arrhenius rate law, e to the power minus e a1 divided by RT. So the AEA1 we have already defined. There is interaction between the molecules and the solid surface. So similarly for case 1, that is be replaced by Ka1 P theta 1 is equal to Kd1. Now it should be theta 2, all right, because for one molecule is coming to sit on the another molecule. So after adsorption, we have the bilayer, so the fraction that is occupied by two molecules. So that's why it is theta 2 multiplied by e to the power minus, now this would be EAL. Why EAL? Because now we are considering the interaction between two molecules, which is equivalent to the molecular interaction between a liquid. So it's a liquid-liquid interaction, so minus EAL, that's why. And then for case 2, we have Ka2 P theta 2 is equal to Kd2 theta 3 e to the power minus EAL divided by RT. So likewise, if we write, so similarly here we can find the case of I minus 1. All right. Why we are writing I minus 1? Because I want to find an expression, general expression involving theta I. So therefore for case I minus 1, we can arrive Ka I minus 1 P theta I minus 1 is equal to KD I minus 1 theta I multiplied by e to the power minus EAL divided by RT. Alright, so now you see we have four different sets of equations and we can call them like equation. So we already have equation 1 and 2, so we can call it equation 3, equation 4, equation 5 and equation 6. Alright, so therefore from this we are going to find an expression for theta I, but we are going to do it a little bit systematically. So before we go further, so we must appreciate one more thing from this set of equation, that is, if we take at the ratios of say KD1 divided by KA1, all right, versus KD2 over KA1 versus KD3 by KA3, and similarly KDI versus KAI. All right, so if we look at these ratios, so these ratios are nothing but rate constant of desorption by rate constant of adsorption, that is, it is the inverse of the equilibrium constant of the adsorption desorption process in the liquid layer. Now since except for the first layer, that means except for this one, for any other multiple layer, these interactions are essentially within between the liquid molecules and they are identical, so we expect that the reverse of the equilibrium constant for the liquid layers only, that means except for the first layer, this should be all identical. All right, and we assume that this is equal to a constant, and that constant is assumed to be something called G, say. All right, so this ratio has been equated to certain constant G, and the the equating these ratios is equal to G is completely logical, because as I said that for the liquid layer, these the reverse of the equilibrium constant or the equilibrium constant itself would be identical. All right, so now we go to our next step, that is, we want to find an expression for theta I in a systematic manner. Why? Because there are certain parity appearing in those reactions. So therefore I'm going to erase the board. I'm going to write the expressions for theta I in a bit more mathematically systematic manner. Okay, so let's do that. Now we have to find the systematic expression for theta I. So for that, what we are going to do, we want to find the expression for theta 1 first. So theta 1 should be is equal to, we can write it over here, that Ka0 divided by Kd0, all right, and then multiplied by P, and then e to the power Ea1 divided by RT multiplied by theta 0. All right, so now what we are going to do, this is a pretty long expression, so I want to condense it, or I want to replace it with a variable parameter y. So since P pressure is a variable quantity, so we have chosen another variable quantity y in order to replace this one. So this is equal to y theta 0. So where, of course, we can write that y is equal to Ka0 divided by Kd0 P e to the power Ea1 divided by RT. All right. So if you so okay, exactly. So this is the value of y. No problem. So then we are going to write the expression for theta 2. So the expression for theta 2 then becomes once again kd1 divided by ka1, and we have p uh, e to the power eal divided by rt multiplied by theta 1. Okay, so now once again we have, you see, another long expression. So and then we can assume that this is another variable parameter x, because so x depends on p, and now p is associated with some other different constants. So we can write it here, this is equal to x theta 1. All right, so then of course here x is equal to, we can have kd1 divided by ka1 p multiplied by e to the power eal divided by rt. Okay, so uh, so did I write it correctly? So no, it should be ka1 divided by kd1. Okay, so it should be like that, ka1 divided by kd1. So if you can remember, this ratio ka1 divided by kd1 is actually reverse of g. All right, so means g was the constant that we equated with this ratio, that is kd1 divided by ka1. So therefore the same thing becomes p divided by g e to the power eal divided by rt. So that is equal to x. So now since theta 2 is equal to x theta 1 and theta 1 is equal to y theta 0, so we can easily write that this is equal to x y theta 0. All right, so therefore now I just have to erase this top part, and I want to write few systematic expression in order to write theta I. So far I have got theta 1 is equal to y theta 0, and theta 2 is equal to xy theta 0. So let's proceed. So I have rewritten the expressions once again on the board. So far what we have got. So since theta 1 is equal to y theta 0, theta 2 is equal to xy theta 0, so theta 3 is equal to, we can expect, and you can also do the same thing, but you can arrive at the same conclusion, that x square y theta 0. So we are adding one term x with every theta we go down. So therefore if we go like that, so of course theta I going to be, so x I to the power x to the power I minus 1 y theta 0. All right, so that is equal to, once again if I break it, x to the power I multiplied by y divided by x theta 0. So why have I written x to the power minus 1 like that? Because I wanted to take a ratio of y divided by x. Why? Further, you see, this is the expression of y and this is the expression of x. So let's take a look what happens if I take the ratio of y over x. So y divided by x becomes ka0 divided by kd0, and then g comes above, so this is multiplied by g, and then the p terms cancels out, and we have e to the power ea1 minus eal whole divided by rt. So if you look at this expression here, ka naught divided by kd naught, or this term is a constant, some equilibrium constant. G, we have already decided that G is another equilibrium constant, so means constant. Now for a particular adsorbent-adsorbent pair, EA1 and EAL are also constant, right? And at a particular temperature, this overall everything, this expression is constant. So therefore, this constant is denoted as C, uppercase C. And this is a dimensionless quantity. You see, if you look at that, so e to the power something is dimensionless. If you can also recollect, G is dimensionless and this is dimensionless. So therefore, this is a dimensionless constant C, and this C is denoted as BET constant, and that C has a very important and decisive role in explaining different kinds of adsorption. So once again, let's come back then. So we can replace this equation with is equal to x to the power I, and in fact we can take the C ahead of this. So this is equal to C x to the power I and theta 0. So that is our expression for theta I. All right. So once again, I'm writing it here. Theta I is equal to C multiplied by x to the power I theta 0. All right. So this is another equation we just got. So now you see we are kind of close. So this is theta I. So we have expressed theta I in terms of a constant x to the power I and also theta 0. So theta 0 sounds much better than arbitrary theta 1, theta I, theta 2, etc. All right. So now what we are going to do, so now we have an expression for theta and the term p itself appears in x. So we are very close to deriving the actual BET equation. So now we have to relate n with theta I. All right. And ultimately with, we have to replace theta 0 ultimately because this is the unknown quantity. So let's see how we can do it. So if we recollect our equation 1, all right, so what was our equation 1? So if you remember from equation 1, so we can write from equation 1, we have n is equal to, if we can recollect properly, that this is I is equal to 1 to infinity, okay, summation of I theta I. All right, so that was multiplied by nm, definitely. Yeah, so that was our equation 1. So, or in order to simplify it, we take n divided by nm is equal to this quantity. Now here, instead of theta I, I'm going to write C x to the power I theta 0. So therefore, this becomes, so we can take C and theta 0 out of the summation term, because our summation term now will have this. So instead of theta I, we have C x I. So this becomes I x to the power I is equal to 1 to infinity. Okay, so yeah, so now you see we have a much simpler expression for n over nm is equal to C, a constant, multiplied by theta 0 multiplied by summation I is equal to 1 to infinity I multiplied by x to the power I. Now this term mathematically converges into some expression. All right, so I am compelled to write the direct expression. Of course you can verify it from other source, that I to the summation of I is equal to 1 to infinity multiplied by I x to the power I. It converges into something like this: x divided by 1 by x whole square. All right, so therefore we can have a simpler looking expression, that is n over nm is equal to something like this. So this is much simpler because we have only x here, C is a constant, but still we have theta 0 and it is unknown. It is not possible what are the fractions of unoccupied spaces. on top of a solid surface. So we have to replace theta 0 by something else with some measurable parameter. So therefore our next job is to find a way to see if we can replace theta 0. So how we can replace theta 0? If you remember, we had the equation number 2. So what was the equation number 2? It contains theta 0. So let me clean the board and let's write the equation number 2, and from that let's try to find out an expression for theta 0. In fact, in order to replace theta 0, we have to do that. Okay, so let's clean the board and do that. Okay, so what we have got, we have rewritten once again. That is the expression for n over nm we just got. And then if we look at our equation 2, so this is not equation 1, sorry, equation 2. So we have the summation of all the fractions is equal to 1. So therefore this one we have already got that theta 0 plus summation of I is equal to 1 to infinity theta I is equal to 1. And of course here we have a relationship between theta I and theta 0. So therefore from this equation probably we can solve for theta 0 by replacing theta I with this. So therefore from here we can get, or theta 0 is equal to 1 minus summation of I is equal to 1 infinity theta I. So here once again we can write 1 minus, so instead of theta I we can write xi, because we can take c times theta 0 out of the summation sign. So that would be summed up from I is equal to 1 to infinity x to the power I. All right. So, or definitely theta 0 is equal to 1 minus c theta 0. So now the question is, what is the value of this? Okay, so the value of this comes out to be 1 over 1 minus x. All right, so now we have this expression theta 0 is equal to 1 minus c theta 0 over 1 minus x. So it's our job to find out theta 0 in terms of c and x. So what is the solution for theta 0? So would you like to try for a few seconds? So if you work it out, so it would come something like this: 1 over x divided by 1 minus x divided by 1 minus x plus cx. So that is our value for theta 0. So now you see we are successful in solving theta 0 in terms of x. Okay, and x contains the parameter p, pressure. So the BET equation is almost formed. So we just have to replace theta 0 with this one. So therefore our n over nm is equal to cx divided by 1 minus x whole square multiplied by, so I have to erase this part, multiplied by, so instead of theta 0 we have 1 minus x divided by 1 minus x plus cx. Okay, so now we have 1 minus x square in the denominator, so this cancels out, and therefore finally we have, so or we can write, we can try right on the top from here. So n over nm takes up the form of cx divided by 1 minus x multiplied by 1 minus x plus cx. Okay, so the equation that we get here, this is the BET, famous BET equation in very crude form. All right, why crude form? Because, all right, so we have n over nm and we were supposed to connect n with pressure. but here we have x. So therefore we have to change the x term into pressure, so then it would have some meaningful thing. So how we are going to do that? So for that we have to remember one thing, that is in terms of adsorption, when the partial pressure P tends to P naught, that means when the partial pressure going to be the saturation pressure, that means the entire surface is saturated with the gas molecules, and you cannot go beyond that, so that's we call the saturation pressure. Then what happens, that N, okay, that means number of molecules, okay, that is that are getting adsorbed, that becomes infinity, of course. So we have a liquid layer on it, so and N is incountable, so that becomes infinity. So likewise what we can see here, that when here x tends to 1, okay, if you replace x with 1, then also N tends to infinity. So that means what? So that means when P is equal to P naught, so that means this x can be equivalent to this quantity P over P naught, which is the partial pressure. So simply, instead of writing directly this the expression of x, which contains P term and G term and etc., whatever it is, we can simply replace x with this fraction P over P naught, because it has the same meaning. All right, because when x tends to 1, N tends to infinity, so we can safely replace x with P by P naught. And if we do so, the same equation takes up the form of this. So, or we can write N over Nm is equal to C multiplied by P over P naught divided by 1 minus P over P naught whole multiplied by 1 minus P over P naught plus C multiplied by P over P naught. Okay, and the bracket ends. All right. So whatever the equation that now we get, okay, so this is called actually the original BET equation. But for the time being, this equation is a bit hard to understand, so we can simplify it. Simplify it means we can exactly represent the equation in Langmuir's linear like equation. So that means there is an option to change this difficult looking equation into a much simpler linear equation. Okay, so whether there we can actually plot 1 over n versus 1 over p, something like that, that we used to do that for case of the Langmuir's linear fit. So the same thing we have to do it here. All right. So the question is, how do we do it here? So for that, again, there are 3-4 step derivation is required. So why don't we quickly do that here and arrive at the linear form of BET equation, and for the rest of the discussion we will use that linear form of BET equation to discuss all the observed experimental adsorption phenomena. Okay, so let's quickly erase this part and derive the linear form of BET equation. Okay. Okay, so let's try to quickly derive the linear form. So this is equal to, of course, Cp divided by P0. So we can take here P0 minus P divided by P0 multiplied by, because we are adding or subtracting everything, P naught P0 minus P plus Cp whole divided by P0. All right. So now this is equal to, so we have P0 square at the denominator and P0 means P0 at the numerator. So therefore this can simplify to Cp naught divided by P naught minus P multiplied by P naught minus P plus Cp. All right, so that is equal to N over Nm. All right. So now what we can do further, that is, or we take the inverse of it, that is Nm over N is equal to P0 minus P multiplied by P0 minus P plus Cp divided by Cp P0. All right, very good. So what else we can do is actually, or we take this part over here, okay, and also we take the P part over over here and Nm part over here. So or we write it here, that is P divided by N multiplied by P naught minus P is equal to P0 minus P plus Cp divided by, so Nm part goes there, so C multiplied by Nm, and we are left with P naught. Okay, so then what we can write also is equal to, so we have P plus Cp part, so we can also make it simplify that we can take P part common multiplied by C minus 1, all right, whole divided by Nm C multiplied by P naught. All right, so now what we can do further is equal to, we can break it down. If we break it down, we get 1 over Nm multiplied by C plus we get, as you can see here, that is C minus 1 divided by C whole multiplied by P over P naught. All right, so if you look at the equation here, so I am bringing it down once again, P divided by N multiplied by P naught minus P is equal to 1 over Nm multiplied by C plus C minus 1 divided by C multiplied by P over P naught. All right, so therefore okay, I think I missed the Nm part over here, so because while transferring it, it should be the common denominator, so the Nm part was there. Okay, so we should have Nm also here. Okay, good. So the expression that I finally found, it is actually in somewhat linear form. What is that? So we can consider this part as y is equal to this part as m, this part as x, and this part is the intercept c constant. So this is in accordance with y is equal to mx plus c form, provided we have to plot p by p naught versus this whole y, then we can form a linear plotting. So this form, whatever we have got, this equation is called the linear form of BET equation. Okay, so the question is, so why did we derive this linear part of BET equation? So now we can explain. So I think we better explain by keeping the two forms, that is the Langmuir form of equation and the BET form of equation side by side, and then we can quickly understand the utility of this. Of course, from this you can understand that from the intercept we are going to determine the Nm part, which is the number of molecules required to cover monolayer, which would be reflected in terms of surface area. All right. So in one last step, we just have a comparative discussion between the Langmuir form of equation and the BET form of equation. All right. So let's quickly do that. Okay. Now, I have written the summarized form of the two results, the Langmuir's models and BET model here, side by side. So now listen to this very carefully. That is, you see, in the Langmuir model, we relate theta with P by P0. And also here, we relate N over Nm or V over Vm with P by P naught. So, and then this is the linear form for the Langmuir's one, and for the BT one, this is these two are the linear form. So one expression is written with respect to number of molecules absorbed, and another expression written with the volume absorbed, basically at the same thing. So let's come to the second aspect. So from this linear equation, linear fit of the Langmuir's model, we would be ready to find Vm from the graph plot, from the linear plot, from the intercept. And once we have the Vm, we can directly calculate the number of moles to number of molecules and the surface area. Same thing happens over here also. Okay, so if we plot y versus, means this versus P by P naught, from the intercept we get a linear equation, and from the intercept we can have Vm and hence the surface area. And also the constant value of C is given here in the expression. So now let's come to the major point. That is, if you look at this expression, if we try to plot N over Nm versus P by P naught, so if you remember that, we plot that, okay? So N over Nm versus P by P naught. So we know that this, following this particular mathematical expression, this would give a plot something like this. And we know that according to IUPAC, this is the type 1 adsorption isotherm. Now, same thing, same type of graph plot can be drawn here also, because with same kind of data, that is, if we try to plot N by Nm versus P by P naught, then we can have the graph plot. But depending on the ranges of P by P naught and depending on the constant C, we will be having the different types of adsorption isotherm. It could be type 1 in special case, could be type 2, could be type 3, could be type 4, depending on the different conditions, okay, which has in Langmuir's equation, there is no provision for determination of type anything other than type 1, but the BT equation, from BT equation, it can be shown that depending on the value of C and other things, different types of adsorption isotherm can be produced and can be explained, and in a certain special circumstances, this BT equation can converge into this Langmuir's form of type 1. So that we are going to discuss in the next class. So experimentally, what we record in adsorption, the machine gives you a data sheet. So the data sheet is nothing but V, volume absorbed at STP, and this, the unit they give you is centimeter cube or cc. All right, and versus you have P by P naught, and of course, as we have seen that P by P naught is a fraction and its maximum value is 1, so it starts with a very low value 0.001 or something, and it gradually goes up. And also the volume at STP gradually changes. So the adsorption experiment would give you only these two data, P by P naught and V. So from that we fit to the equations, and so if we directly plot this, we according to this equation, we may get different results. Okay, and if we try to plot with this, we may get different results also. So I think we stop it here. So in the next class, we are going to see that how from one single BET equation we can explain the 4 different types of adsorption isotherm. Okay, so but remember, experimentally you're only going to get these 2 data. So but you need the BET equation to perfectly fit that, and from that, if your fit is correct, then you can give the correct information of the surface area. So I understand that it took quite a bit of time to derive the entire BET equation, but trust me on one thing, in no readily available physical chemistry textbook would deal with this derivation. They would straight away give the result. So the derivation is very rare to find. So I hope that I would put that up in one single place and it would stay there, and whenever you require it in future for whatever reason, we can readily refer to the BET equation itself and its derivation. So I hope you have a better understanding that how the BET equation evolved, okay, the underlying physical significance. Okay, so I think that's enough for today, and stay safe and take care of yourself, and we will see you in the next lecture. Till then, goodbye.